Welcome to video number 5 of our jet engine series. On our last episode, we saw the equations for the compressor, as well as some of the limitations we will face with a simplified model. On this video, we'll start coding where we left off from the inlet. Let's dive in!
3, 2, 1, top.
3, 2, 1, half, the Flight Test Engineering channel.
If you want to follow along, you can access the Flight Test Engineering GitHub site. And then in there's going to be the gas turbine propulsion repo. And if you access that, there's going to be the Turbojet subdirectory. And in there, you will find the episodes 4 and 5 compressor notebook. If you check it out, it's going to have all of the equations there, and also all the code that's going to be represented in these 2 episodes. And if you want to download, you just access this button here, and it will download directly to your desktop. We had left off on video number 3 with the inlet coded in our notebook here that I have open, just to recap. So we had all the theory on the top here, and then we have the preamble that we ran. Remember, we put our helper functions on a separate file, and then we had the parameters that were defining the engine physical parameters, and then the performance parameters. And also we defined our iterative inlet function here that we ran. Also the engine operating conditions were set and defined here. And when we ran all this at the end, this is for station A to station 1, and for station 1 to station 2, we got this graph here which shows how the pressure rises as the air gets compressed in the inlet, and how the temperature also rises altogether. So starting from this notebook, let's build our compressor now. First, let's define the engine parameters that we're missing for the compressor here. So the first thing that we're going to do is add to our engine parameters the number of compressor stages that we're going to have. In this case, let's define as 10. That will give us a pretty low rise on the temperature per stage, and also is the number of stages that we have on the Oranda. Next up, we're going to have the compressor pressure ratio. We're going to define it as 6.1. Again, this is what we have on the Oranda. And the eta C, this is the isentropic stage efficiency for the compressor. We're going to define it as a low number here, 0.8. Because again, this is an old compressor, and that's pretty much what was typical in that stage. So let's run the cells up to here to load our compressor. So we can do run cells above selected cell. All right. And then looking at this cell that is hidden here, this is exactly the cell that we had before for the inlet iterative function. So we can load that in. These are just the formulas that we saw before. Here's going to be, we're going to come back to this cell in just a second. Let's run also the ambient conditions, which is the same cell we had before, still Mach 0.8 at 35,000 feet. Same thing for the initial stations. And here is the calculation from station A to station 1 of our inlet. We had in our last video, our video number 3 as well, this nice plot going from station A to station 1, and also from station 1 to station 2, we had this plot. So now we're ready to go and look at the implementation of our compressor, which is in this function here. We'll code our compressor with multiple stages, and we'll try to make the temperature rise across all of the stages as constant as possible. So that's what I mean by constant temperature rise here. For inputs, our compressor needs to receive, well, the gas properties. Here it's going to go in our gas in Cantera object, the number of stages, the compressor pressure ratio, the efficiency that we saw that we're going to pass in only 1, the Mach number going in so that we can calculate all the 3 stagnation properties. And just like we did with the inlet, the gas out object here, so that we can pass back our results. Remember that the efficiency will vary according to the RPM and mass flow, and we would have to have the compressor map in order to figure it out properly. But we don't have it. So for now, we're going to go simple and just stick with a fixed value. But in a later video, we'll use other codes done by brilliant people at NASA Glenn to come up with a much better model of a high bypass turbofan. Stay tuned for that one. Okay, first things first, we need to calculate the input gas property. So just like we did again on the inlet, we calculate the gamma in and store it on this variable. And we calculate the stagnation temperature and stagnation pressure of the gas going in, given the input gas temperature and pressures, static pressures, the gamma that we just calculated, and the Mach number going in. Now, we need to figure out what is going to be the pressure ratio per stage. And we can calculate the calculated ratio per stage as being the n stages root of the compressor pressure ratio, overall compressor pressure ratio. That's going to be stored on this variable here. This is a way that if you multiply this number by n stages, you get the CPR at the end. Okay, now let me explain how we're going to equalize the temperature rise as best as possible. The strategy here is to calculate all the stages, then check for the maximum temperature rise. And if it is more than the previous iteration, we shift the pressure ratio increasing in the front and decreasing in the rear, but in a way that the overall pressure ratio is kept around what we are aiming for. To do this, we create a vector of ones and call it the stage multiplier, which is right there. And the amount of shifting we'll do per iteration is defined next. So this is the shift. We're going to shift 0.1% per iteration. We want to go slowly since this is not really an optimization. I mean, we could create a function here to invoke a super duper algorithm to optimize the thing, but for our toy example, I think that would be an overkill. So keep it simple and we'll slowly shift until we approximately find the minimum. To calculate the shift at each iteration, we create another vector, which I call shifter, which is right there. And the idea here is that we multiply the stage multiplier by this shifter every iteration, effectively increasing the pressure ratio at the front and decreasing at the rear. Now, from one stage to another, we need a step shifter, which is going to be the amount we want to shift, the 0.1%, divided by the number of stages. So that's what it is right there. But we need to go up on one side, meaning the initial stages of our compressor, and go down on the other side. The center of the vector is estimated by taking the integer division by 2, right? This is the number of stages divided by 2 and taking the integer. And it will not matter if the vector has an even number of elements, and it will work fine at the end because this is just an approximation. And next we populate the shifter by attributing values that are higher than 1 for the first half and lower than 1, but still positive for the last half, so that when we multiply, the pressure gets shifted forward. Next, we create the variables that will control our pressurized shift loop. We create a variable to control if it has converged. The number of iterations are going to be kept on this one, and this is going to be our maximum number of iterations that we allow. The initial value of our convergence check, which will be the delta t, we start with a ridiculously high number to guarantee that the first iteration goes through. I prefer it this way because then we do not have to do an if statement being run every iteration and checking if this is the first step. For the stage properties, we create two vectors here that will hold the pressures and temperatures for each stage. This will allow us later to calculate the maximum temperature rise and, for example, as well as pass these values back to the plotting function that we had before. We also create an internal gas object that will propagate from stage to stage and set its composition to air initially, because that's what the compressor is going to compress. Last, we need later how much work the compressor has done. So since we already are going to have it calculated per stage, we just create a variable here that will collect how much work we are inputting to each stage, and then at the end of the function run, we'll have this number already at hand. Okay, so now we start our pressurized shift loop. We start by saying that we're going to run it while it's not converged, and also while our number of iterations has not reached the maximum. We start by setting the stage gas to the initial properties, so our gas in, temperature, and pressure. And then nothing better than a for loop to calculate the properties for each of the stages. Because we know how many stages we have, this would be the most efficient way to do it. We keep here the initial temperature that we have, our TI, before the compression of each stage, and to calculate the work at the end of the loop. Also, we're going to use this. Then we calculate gamma for each stage, because this is running per stage. We calculate gamma. Then we calculate the total pressure, P0 here. And as we saw before, but note that the pressure ratio is multiplied by the stage multiplier, which is right there, right? It's the pressure ratio times the stage multiplier. If that's effectively changing how much the stage is compressing. Remember, we're shifting towards the front. Last, we calculate the total temperature using the pressure that we just got, the P0. We get the static values and update the stage gas. So this is what we're getting, the static values, to update the stage gas with the temperature and pressure that result from that. Then we recalculate the gamma here, because the temperature and pressure have changed. And this is also because here we have a chicken and egg dilemma. To get the new static temperature and pressure, we need the gamma, but we only have gamma if we update the gas with the static pressure and temperature. So we do this 2 times. Get the gamma here, we calculate temperature and static pressure and temperature, recalculate the stage gas, get the gamma again, recalculate static pressure and temperature, and update the stage gas again. I have toyed around with this before, and I found out that 2 times is close enough. We could do a function to do this, or do it more times, but I found out that 2 times is close enough. So again, we get the static temperature and pressure with the new gamma and update the gas properties. Then we calculate the work required, work that we inputted to this stage here, which is going to be our Cp times delta T. And we update for the next stage. We say that our static pressure in and our static temperature in is going to be the static pressure and temperature that we just calculated for the stage. And the loop runs again until you reach the number of stages here. When we have all the stages finished, we get the maximum delta T here. We need a few conditions here to treat the edge cases, 1 and 2 stages. If we have many stages, more than 2, then it's easy. We just use NumPy to calculate the differences and give us the maximum straight. We don't have to do anything else. But if we have more than 1 stage, meaning that we have 2 stages, we calculate the maximum between our last stage and our intermediate stage, and our intermediate stage and our initial temperature of the gas going in. And if we have only 1 stage, then the edge case is going to be our end temperature minus the temperature going in. That will all end up giving us the maximum delta T that we have for this iteration. And then here, if our maximum delta T is less than our previous delta T, maximum delta T, and the number of iterations is less than the maximum, then we go again and run the loop again. We increment the number of iterations. We clear the previous data and reset the inputs by setting our static temperature and pressure going in as the static temperature and pressure of the gas that we said is going in. We zero in the compressor work because the compressor work that we calculated is no good. And we shift the stage multiplier one step more to the front. And also we say that our previous maximum delta t is going to be the maximum delta t that we just calculated. And we iterate and go again and calculate the loop. So you see that we're going to keep doing this until either our maximum delta t for this iteration drops in relation to our previous maximum delta t, meaning that we're moving the pressure ratio too much to the front, or we reach the maximum number of iterations. Until then, we keep shifting until we reach these conditions here. And if we have reached the maximum number of iterations, we throw out a flag saying that we did not converge. And if we did converge at the end, we set the flag to true, and we print out a message stating how many iterations were necessary and the maximum delta t. And at the end, what we do is we update the gas going out with the pressure and temperature that we just calculated, and that is passed back to the calling function. Okay, now we're ready to run the code. Let's see how it goes. Let's load the function that we just implemented. These are the ambient conditions we had run already. And we already have this. Let's go to the cell that runs the function here for the compressor, which is right there. These are the cells that we have. And I'll explain them. Just hold on for a second. So this is where we're going to call our function here. We're going to get back our stations out, our convergency flag, our compressor work, and we're going to call our multi-stage compressor, passing in the gas number 2 that we got from station 2. We pass in the number of stages, the compressor pressure ratio, our eta C, the Mach number going in from station 2, and we are going to store everything that we get from this compressor on our gas out, which is going to be gas station number 3. And so if we run this, and at the end we update and append the values that we get for the temperatures, pressures, and also for our gas composition on our lists that we use to plot the results down here on the next cell. So we can see that the compressor finished, it converged and used 77 iterations, and the maximum delta T between stages was 22.1 Kelvin. So this is pretty good. It's you see, it's not linear. We had to bring in the pressure quite a lot to the front in order to achieve a maximum delta T that is reasonable between all of the stages. So now the last stage that we have here on our code is that we can print out the stations and also create our graph with the data that we just got. So let's see what we get. The interesting values here are that we go from our pressure at station A. Remember, we're flying at 35,000 feet. So we had our pressure at 0.24 atmospheres. And now at the exit of our compressor, we are almost at 2 bar, 1.92 atmospheres. Notice that the Mach number didn't change. We're not messing with the Mach number here. We're just assuming it's the same. But the temperature also rises a lot. So we started at 200 Kelvin and we're now at 452 Kelvin. Notice also that the entropy was constant in the first transformation that we had, because remember, we assumed that there was no loss between station A and station 1. And then from station 1 to station 2, there was loss. So the entropy has risen just a little bit, but it has risen. And now for the compressor, we know that we have losses. And so the entropy rises a lot. Not a lot, but it rises considerably. So this is the graph that we get here. Remember, we were at ambient conditions here. We get the first compressor compression outside of the inlet just by slowing down the air. Then inside the inlet, we get this double thicker line here. Then as each stage of the compressor goes, we rise the pressure just a little bit, and this is what we get at the end. Together with the rising pressure, we get, of course, a rising temperature and a rising entropy here, right? So this is what we get. And this brings us to the end of this video. If you want a copy of this notebook, please visit the channel's GitHub page. The link's going to be down below. And thanks for sticking around with me until now. And on our next video, we'll go for the hot stuff. Let's write the combustor module. See you there!